Hello students, in today's video we're going to be working on linearization and Newton's method. So let's get started. Go ahead and try this quick warm-up problem and we'll go ahead and move on from there. Hopefully you paused your screen and you're just coming back right now to check your answers. Hopefully you didn't find this to be too difficult, but here's the essential part. It says that we were given a swimming pool with area 1800 square feet. And we know that the area of a rectangle is length times width, or in this case, x times y. Next thing they mention is we want to add to this property. So we need to rearrange our formula. We're going to say we need to take our area and take our x, and we're going to add 10 feet to both sides. So that's 10 feet on one end, 10 feet on another, so that's 20 total. And on the other side, we're going to add 5 on each end, so that's a total of 10. And so now, since we're trying to find the smallest piece of property, or the minimum, we need to take the derivative of this formula that we have here. Again, the only problem though is that we have two different variables, which is not okay. Now, because we wrote this formula earlier, that 1800 equals x times y, we're going to go ahead and solve for y and get y is equal to 1800 divided by x. The reason why we do that is because now we can substitute that back into our equation. And we have the following equation. Now, to make things a little easier, we're going to go ahead and distribute, and we get 1800 plus 10x plus 36,000 divided by x plus 200. Now we're going to go ahead and find the derivative of each piece, and that turns out to be 10 minus 36,000 x squared. And because we're trying to find a min or a max, we set this equal to 0. And in the end, we get x is equal to 60. Now we know that x is equal to 60 feet. We could substitute that back into the original equation and find that y is equal to 30 feet. Final answer, it says find the smallest piece of property. So keep in mind, we just found the lengths and widths of length and width of the pool. We need to answer the question of what's the smallest dimensions for the property, which must be 80 by 40, because we substitute our 60 and 30 back into equation at the top and find the length. We basically added 20 and 10 respectively. So that's how we maximize or minimize the amount of property we have to purchase. So now let's go ahead and look at another problem. Here, write the equation of a line tangent to the following. So remember, when we're trying to solve equations like this, we want to go ahead and first substitute that x into the original. So we're basically trying to find f of 0. We find that that turns out to be equal to 0. So we know that when x is equal to 0, the graph is equal to 0. Next thing we do is we find f prime of x. F prime of x turns out to be 1 divided by the quantity x plus 1. We substitute that 0 in to find the slope of the tangent. And we get 1 divided by 1, which is equal to 1. And finally, use point slope formula to find the equation of a line. In this particular case, it turns out to be y equals x. So that's how you find the equation of a line tangent. So again, we're working on linearization and Newton's method. So let's talk about linearization for a second. Now, linearization states that if f is differentiable at x equals a, then f is locally linear. Keep in mind, linear sounds exactly what you think it sounds like, line. Now, basically, the process of linearization is zooming in very close so that the function f looks like a straight line. So essentially, we're taking any function, and during the process of linearization, we are zooming in so much that it looks like a line. So the linearization of f at a is denoted by this following formula. L of x equals f of a plus f prime of a times the quantity x minus a. Now the approximation of f of x is approximate to L of x. Now that's the standard linear approximation of f at a. So we're going to go over this kind of quickly because it is a BC topic. We wanted to make sure we exposed you to it. So in this particular case, we are going to find the linearization of f of x equals the cubed root of x at a equal to 8.5. So this is actually not as bad as you think. And again, we're not going to spend too much time on it, but we want to make sure you're exposed. So remember, we're going to stick to the formula. L of x equals f of a plus f prime of a times the quantity x minus a. Now, as a side note, we know that, well, let's go ahead and just start substituting these things in. We're going to find the cubed root of 8.5. Notice here we substituted f of a. F of a is cubed root of x, and since we know what a is, 8.5, we're going to substitute that in, plus f prime of a. So we know the derivative of the cubed root of x is a 1/3 times a to the negative 2/3 power times x minus 8.5. So once you found this, you've gone ahead and evaluated. You found the linearization of f of x in this particular case. So what I'm going to go ahead and do is add another example problem for you, just to make sure we're clear. We're going to do the same thing, but this time we're going to call f of x the square root of x squared plus 9 at a equals negative 4. So again, we're going to stick to the formula. L of x equals f of a plus f prime of a times x minus a. So we know that L of x is equal to, now we know it's the square root of x squared plus 9. So you have the square root of x squared. X in this particular case is negative 4. So negative 4 squared is 16 plus 9 plus f prime of a. Now we know f prime of a, or the derivative of the square root of x squared plus 9, would yield negative 4/5 times x plus 4. Now we know that approximation, when we clean this all up, turns out to be 5 minus 4/5 x minus 16/5. Simplifying further, we get negative 4/5 x plus 9/5. Now, the last thing we want to do here, sometimes they'll ask us to approximate with a plus 0.1. So when they ask us to approximate with a added piece or added value to the center, we're going to go ahead and substitute that in. So negative 4/5 times 0.1 plus 9/5. That turns out to be 5.008. So if we take a look at that, that's the same thing they asked us to do here in this part of the problem, which I didn't show you on purpose. Notice here it says L of a plus 0.1. That's the same thing we did here when we did this linearization. So again, this is more of a just plug and chug more so than you need to understand it, because you're not going to use it too much. It's more of a BC topic, but we want to make sure you've been exposed. So now we want you to estimate the square root of 25.1 without a calculator. So Following this, when they give you these specific values, you want to look at a center. What's the nearest number? So we want to find a center. Now your center should be the closest number to this number, 25.1, that has a square root. So the nearest number to 25.1 that has a clean square root is the square root of 25. So our center is going to be at, so center at square root of 25. Now we're going to go ahead and use the approximation formula for linearization. We get L of x equals f of a plus f prime of a times x minus a. We know that f prime of a, because our center is a, is the square root of 25 plus the derivative of square root of x turns out to be 1/2 x to the 1/2 power times x minus a. So notice I purposely didn't put in the a to start with. So we have square root of 25, which is just 5, plus 1/2 5 to the negative 1/2 power times x minus 5. We end up getting 5 plus 1/10 times. Now, notice our x value is the original number, so the 25.1. So now we're going to substitute this in and say 25.1 minus 25. Sorry, this should have been 25 too. Now we get 5 plus 1/10 times 0.1. We end up with 5.01 as our approximate to the square root of 25.1. Again, we're using these as approximations. You're being exposed because really we could just do this on our calculator. Now, let's take a look at Newton's method. Newton's method is another method for us to find the zeros of a function. It basically uses linearizations to find these zeros. Now the process repeats until the answers converge. So basically, we're going to continue to do this process here until we get to a number that's very close to the exact answer. And this could be done hundreds of times. But we're not going to do it that many times. So, Newton's method says step 1, we're going to guess an approximate root, 0, or x-intercept. We're going to use the first approximation to get a second approximation, and use the second approximation to get the third, and so on. So the important part to notice here is that we're going to use this formula given the function that we're given. But step 1 is the most important. We're going to guess an approximate root. So it could be any number you want, as close to the number or as far close to the number, the better it is going to be for you, because the less time it's going to take for us to find that solution. So let's go ahead and look at example 3 here. F of x equals x to the 4th plus x minus 3. Now, sticking to the formula, we get x sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n minus 1. Okay, so, f of x sub n. So, given the function, we know that f of x is equal to x to the 4th plus x minus 3. We know f prime of x is equal to 4x to the 3rd plus 1. So, sticking to the formula, we have x equals x sub n minus x to the fourth plus x minus 3, all divided by 4x to the third plus 1. Now, we asked you to take a guess at this. So that's exactly what we're going to do. Now, keep in mind, we're going to look at the graph just to make this a little bit easier for us. So what we're going to do is we're going to turn on that graph, and notice I'm using Desmos. You could do this on your graphing calculator. So here's the function. Now, it looks like these answers are close to 1.5, negative 1.5 here. I know it's obviously not exactly on it, but it's close. And on the right side, we have what looks like could be 1.2. Now, notice I graphed these because it's going to be easier to find them. Okay, and those are our guesses. And because we graphed the original, we know that there's two possible answers. Now, we set up this formula right here. And what I did to make this a little bit easier is I went ahead and graphed this for us now. So I'm going to turn on the graph, which you're going to see in purple. Now, what happens here is once we have this graph, notice I wrote down the equation here, we can start selecting x values. So what we did is, according to step 1, we guessed. We guessed that it's about negative 1.5, which is why I substituted in for x here. And when we did that, it sped out this value for us, negative 1.455. So what we did now is we then took this negative 1.455 and we used that for our x. And then when we substitute that value for x, we got negative 1.4526332. We substituted that into here, and we got this final answer. So notice that we've done this a total of 3 times. We've substituted once, twice, and thrice. They ask us for 6 approximates. We would do this 3 times. Notice how substituting this into your calculator kind of is time consuming. So if you do this using the table like I showed you here, or doing the calculate table on your TIs, this would become much, much, much easier. Now, if we wanted to, because we said there was 2 answers, we could also substitute 1.2. Notice 1.2 yielded 1.1654196. And then we use that same value, the y value that we just got, 1.1640373. And then we could do it again, 1.1640351. And notice we're getting closer and closer and closer to our answer. So, this is how you would do all these approximations, both linear or using linearizations, and then we can use linearizations to use Newton's method. So, let's see something that's much easier for, I think, much easier for everybody. So now we have this idea of differentials. Differentials are like small deltas, and finding a differential is similar to finding a derivative. So, let's go ahead and do that with example form. It says find the differential dy for y equals cosine of 3x squared minus 5x. So, first things first, pretty simple. We're going to go ahead and take the derivative. So we know that y equals cosine of 3x squared minus 5x. We know that y prime is equal to sine of 3x squared minus 5x times the derivative of the inside, which turns out to be 6x minus 5. And now we found our differential like it requested in part A. Now part B, it says evaluate dy at x equals 2 and dx equal to 0.1. So the one thing I forgot to add here is since we found these derivatives, I forgot to add a dx at the end, which is really, really important. Okay, so anytime you find the derivative of anything, you just add a dx at the back end. So now that we have this, we're substituting the x and the dx value in. So y prime equals sine of 3 times 2 squared minus 5 times 2 times 6 times 2 minus 5 times dx. Now dx in this particular case is 0.1. So when we clean this up, we get y equals sine of 2 times 7 times 0.1. Finally, y prime is equal to 0.7 times sine of 2. And that's our final answer. Let's do this one more time. This time I'm giving you a general equation that you need to solve for. It says write a differential formula that estimates the change in surface area of a sphere when the radius changes from a to a plus dr. So notice it says surface area of a sphere. So surface area of a sphere is 4 pi r squared. So you find SA prime, that turns out to be 8 pi r dr. Remember, don't forget that dr. So we have 8 pi times, notice it says from when the radius changes from a to a plus dr. That means instead of using our radius a, or r, we're going to use a. And notice the dr, remember d stands for delta, and delta means the change. So if you look at the change, it's changed from a to a plus dr. That basically means it changed dr much. Notice I substituted this dr or this dr because we were given it here in the general formula. Okay, if it's at dA, then this would essentially say dA. So let me repeat that. If this had a plus dA, then this would say dA here. So I know this is a little confusing, but you're going to have time to practice this. And again, I just wanted you to be exposed. But that's all for now. I'll see you guys next time.